Hello, I'm Mark Pollitt, and the title of this presentation is The Hierarchy of Access, a way of looking at digital evidence. Don't let the word hierarchy bother you. It really is about a way of looking at digital evidence. Most textbooks, most books on digital evidence, and most training programs in digital evidence tend to focus on the particulars, whether it's data recovery from file systems or application data recovery or metadata and those sorts of things. But the problem with focusing on the details is that as the technologies evolve and as the people who use these technologies use them in different ways, it becomes important to be able to adapt your forensic process and your tools to the new realities. And so most textbooks, most instructors don't provide a framework for looking at digital evidence. And so my point in this lecture is to give you that kind of a framework that you can apply to any digital forensic problem, even if it's a new technology. And so we're going to look at it in that fashion. Most of you have seen what is commonly known as a Matryoshka doll, very common in Russia and some of the Middle Eastern countries. Those of you that have seen them know that it is this external doll that very often contains other dolls. Thus we see it deconstructed, if you will. Well, computers are a little bit like that as well. They really are a series of layers, and we're going to deconstruct those layers one layer at a time, and that's what this hierarchy of access is about, is this deconstructing a computer problem or a digital evidence problem one layer at a time. Another way to look at it is like an onion. If you were to think of the outside of the onion as being the physical media and the core of it being the actual content of the individual files, you realize that the media has to be formatted, it has to be accessed by an operating system which has to understand the file type, which has to have an application that understands that particular file structure, and then have the actual data itself. And so you have to go through all of these layers in order to get to your ultimate data. Well, each of these layers is a technology, and each of these technologies have forensic value, meaning that there are things that we can learn from each of those. And if we understand what each of those layers can and cannot tell us, then we have a better understanding of the actual data, and we know what we can rely on about that data and what we can't rely on. Because ultimately, if you can't rely on the things that surround the data, then you can't rely on the data itself. I came up with this list somewhat arbitrarily, but my kind of perspective when I came up with this list was to kind of start with the nut behind the keyboard, the user, and go, okay, what does the user touch, what does that touch, and what does that in turn touch, all the way up to the electrons that are in there at ones and zeros. And so I came up with this list, and we're going to look at each of these lists, or each of these items one at a time. And some of them are more valuable than others, but the important point is not how valuable they are. The point is that we recognize that there are these layers, and that we ask the question about what can these layers tell us, if anything. If it weren't for users, the standing joke in IT support is, if it weren't for stupid people, I wouldn't have a job. Well, if it weren't for stupid criminals, I wouldn't have had a job as an investigator or as a forensic examiner. But the good news is that there are a lot of smart people out there, and there are also a lot of good people that can help us in our digital forensic cases. And case in point, I had a challenge one time to do a digital forensic examination of an entire corporation. It was a very large defense contractor, and it would have taken forever to do this work. But fortunately, I interviewed a bunch of people before I started doing digital stuff, and one of the people that I talked to was the systems administrator, who informed me that just the previous evening they had done a corporate-wide backup, and that backup would be available on a tape right about the time I was interviewing her. And so we went and retrieved that tape and initialed and dated, put it in an evidence envelope, and we were able to dispose of a good portion of the digital forensic work. Now, there was other work that still needed to be done, but that eliminated thousands and thousands of hours of work. And so understanding our users, good and bad, is really important. And if you don't know anything about the user of the system that you're going to examine, then you're really operating at a disadvantage. Conversely, you should be thinking in terms of, who can help me understand this evidence? Is there somebody that we can trust that understands the individual, the scheme, whatever it is? Then that may be really useful. Another example of that is I had a case involving a large fraud, and we understood the scheme. The investigator understood thoroughly what the scheme was. The trick was, how are we going to figure out how many of these things they did and how many victims were there, etc. And while we had seized the company's database, it was a proprietary database, and it had a limited number of features that would have helped us to figure out who our victims were and how much of this went on. So what we did was we contracted with the author of the actual database, and I basically sat as the interpreter between the programmer and the investigator until we were able to write some queries and compile them and run them on the database, and were able to basically get a printout of exactly what it is that we needed to make the case. And so understanding that users are a part of computer systems, and therefore as forensic examiners we need to include that is part of our understanding of the case and how we work on a case. Now, the computer itself is kind of an ironic situation. At one level, if it weren't for computers, we wouldn't have many digital evidence cases. But the flip side of it is computers themselves are hardware. They're just material. Now, in some cases, what hardware is attached makes a difference. If you're trying to prove a counterfeiting case, having the same kind of printer attached, having Photoshop and having scans, having a scanner there, may prove to be useful evidence. But for the most part, the best evidence that you very often get out of the physical computers is not digital evidence, but physical evidence. And very often we forget that there is physical evidence there. The DNA that we can get from the keyboard and what's underneath the keyboard, the fingerprints that we may be able to find, the blood that we may be able to find from where they've removed boards and that sort of thing on the internals, all of these things are physical evidence that may in fact be very useful to us. So we need to remember that the computer is both a physical object and therefore has physical evidence, but it also has some limited role in terms of the actual digital evidence. People buy computers, whether it's a PC or a Unix box or a Macintosh, very often because it looks cool. But the reality of it is, if it doesn't have the applications in the operating system that they can use, it's useless. So really, people don't buy computers, they really buy them for the next two items on our hierarchy of access. Ultimately, people buy computers because they want them to do something. And the thing that actually does something that is very often the goal of the user is the application. And marketers have done a very good job of convincing users that they need not only all kinds of applications, but they need to update those applications and to buy new applications that have more features. But as we'll see shortly, features to a forensic examiner are another name for evidence. Because what features really are is making the software easier to use for the user. And so by making it easier for the user, it essentially knows more and stores more information about what the user is doing. And in the process is very often protecting the user from doing dumb things, and at the same time automatically doing and recording things for the user that they might not have thought to do on their own. And so these application features that make them faster and better and more user-friendly leave a whole collection of pieces of evidence, artifacts, if you will. As an example, standard word. I write a letter, my dear sir, whom I despise. I realize that, maybe that's not such a good idea. I'm sending this letter to my boss, so I delete that and I go on and I continue and I write the rest of the letter. And I email that letter to my boss. Unfortunately, my boss has taken this class, and he knows that if he looks at the actual Word file with a hex editor, what he will see is not only what I wrote, but what I deleted. And fortunately, it even signs it for me. So this is an example of a feature where the software is trying to protect the user from inadvertently deleting things. And it says, hey dummy, you might not really have wanted to delete this, so I'm going to save it for you just in case you really didn't mean to do this. And so by protecting me from my own stupidity, it basically is documenting my evidence of what I did. This is merely one example of the kinds of debris that applications leave behind, all in the name of features. There's a whole set of metadata, which is information about information, that are not only created by the file in the operating systems, but are actually created by the applications themselves. This is an example of some of the metadata that's created by PowerPoint. And it not only has the standard modified access and created dates, but it even keeps the data of when it was last printed. It says how many revisions there were, who was the last person to save it, what was the total editing time, all of these sorts of things. Any of those things might be very useful, particularly if you're looking at a file that has had its modified access and created times altered, but yet the person that altered those through the operating system wasn't aware of the fact that the application kept its own metadata, and that if that metadata conflicts with what they are trying to show in the operating system metadata, it could be a pretty good indication to you that there's a rat here someplace. Likewise, most users are not aware of the internal metadata in the files, and therefore you may be able to find information of value that will either confirm or deny some particular process or scenario that a user claims. Now, applications run in operating systems, and operating systems are very simply the hardware, the software that connects the hardware to the application in its simplest form. It provides all of the services that are needed by applications, at the same time feeding and taking care of the hardware that makes up the actual computer itself. And operating systems have evolved over time, and a great example of that, I think, is Windows. If we look at the evolution of Windows from its earliest form, Windows 3.1, to today's Windows 8, it's a millennial difference between the two. But interestingly enough, at their core, they do exactly the same things. They just do them differently. And aside from the look and feel part of it, operating systems are just like applications in that they're marketed primarily for the use of a bunch of features. Windows 8 has a bunch of features that Windows 7 didn't have. Windows 7 had some features that Vista didn't, etc. And as we've already understood with applications, those features really equate to, in many cases, evidence as well. And you may not necessarily think of it this way, but as you're trying to learn what evidence is available in a particular operating system, consider operating systems leave all kinds of debris, such as recently used files and temporary internet files and logs and cookies and cache files and spooler files and registry entries. All of these things are used by the operating system to keep track of information. And they're all done with the goal in mind of making the user experience quicker and smoother and more intuitive. And so every time a new operating system comes out, you want to look at that operating system and say, okay, what features does this operating system have, and how are what debris does it leave as a result of those features, and how do I access those, and how do I interpret those? And virtually all courses in digital forensics talk about things like cache files and registry entries and temporary internet files, but there are others as well. And whenever a new operating system comes out, one of the questions you need to ask is, okay, what kinds of things like this are going to be available to me as a forensic examiner, and how do they work? Temporary internet files. This is an example of what one of the directories look like. It's obviously a very old one, IE5, but it's really no different than the new stuff. But we have software now that's much better at putting these together and putting them into a chronology, and all of that's well and good. But before anybody wrote the software to make looking at internet histories very easy and to be able to mine the cache very easily, somebody had to realize it was there and start looking at it and try to figure out how to put it together. And so as an examiner, you very well may find yourself in the position where you're having to look at how a new operating system, or an operating system for which you don't have a lot of data, operates. You need to start looking for these sorts of things. So that's really an important element. Registry entries. The same sort of thing. In the case of the Windows registry, there are thousands and thousands of entries, and so knowing what entries are useful and what entries are kept is a challenge. And so these are the kinds of things that are done in the name of convenience and in the name of efficiency, but they all leave trails behind, and you very well may find yourself needing to look at those trails. More and more operating systems have the ability to read multiple file systems that are not its native format. And applications are getting a little bit better at doing that, or forensic applications are getting a little bit better at reading file systems. Technically, file systems really are completely separate from operating systems. There's absolutely no reason why you could not have written Windows 7 to have a native operating system of UFS, which is a Unix file system. They chose not to, but there's no reason that it couldn't have. Instead, NTFS was the standard methodology, but it also reads all of the FAT variants as well. So file systems are very often associated with operating systems, but it's important to realize that they really are separate. And it's also important to understand that the relationship between the operating system and the file system is different. For instance, if you mount a Windows native file system like FAT or NTFS on a Linux operating system, yes, it will read it, but it will do some very strange things to the dates, because the dates are not done the same way in Linux as they are in FAT and NTFS. And so you may well find yourself with some very strange dates in there, and it's entirely because of the way the operating system interacts with the file system. So understanding how the file system works and preserving the file system and being able to look at the file system through, for lack of a better term, native eyes is really important. This is why I'm not a big fan of doing forensic examinations on other than native file systems. I think it's a little bit tricky, particularly when it comes to dealing with dates and times and that sort of thing. But this is the normal view that people see of file systems. It looks very neat, like file folders and all the rest of it. It's really not, and understanding exactly how that works is really important. A good example of that is Slack. Slack is not at all intuitive based on looking at the standard folder model of a file system. In this particular case, we're seeing an example of Slack in the context of a FAT file system, and particularly one that was native to Windows 95 version 1. And all of the Windows and DOS versions prior to that actually had two different kinds of Slack. They had memory Slack and drive Slack. So that when a file was stored, it used multiple allocation units. That anything left over in terms of space from the file in the first sector of the allocation unit was automatically padded with data from RAM. And so you might very often find some interesting things that were never intended to be saved in memory Slack. That has gone away since Windows 95 version 2, but it is interesting from a historical perspective, and there's nothing to say that it might not operate that way in some other file systems, particularly as we start getting into tablets and smartphones and that sort of thing. Drive Slack are the remains of a file that was there previous to the storage of the new file, and is just not overwritten data. So understanding how the file system actually operates allows you to not only find this data, but to interpret it and be able to explain it on the stand. Deleted files. We know that the standard FAT file system utilizes a file allocation table, and it stores the directory entries, and it uses hex-E5 or Sigma to indicate an erased file. All of this is good, but you can't interpret this stuff if you don't understand how the file system works. And so that's why it's really important that we have books like Brian Carrier's File System Forensic Analysis, because he has taken the time to figure out how all of these things work. The bad news is that as we get more and more into smartphones and portable devices where memory is very valuable, and we're using newer technologies, solid-state storage devices, etc., the old rules kind of go away, and so you may find yourself having to figure out how it works. And so this is an example of why you really have to step through each of these layers and go, okay, how is this different from the things that I'm used to working with? The file itself. Now, there's two aspects to that. At one level, a file is what it is. It's a bunch of ones and zeros that are either interpreted as ASCII or as executable or as data through some form of interpretation. As an example, the earlier versions of the Microsoft Office suite stored their files, for instance, for Word as .doc, and it was a proprietary format that had a file header that says, hey, operating system, and hey, application, this is in fact a Microsoft Word 95 document, and interpreted accordingly, and it understood how that file actually stored the data, and so it could recreate what it was that you intended in terms of the document. The newer versions, the ones that end in X, the docx, etc., are stored in XML, so that they basically have a file system within a file system. That's also true of some other proprietary data formats, such as PDFs. PDF files are really a little file system in and of themselves that will store images and text and formatting information, etc., in a standardized way that the application understands. And so the ability to not only extract the data from a file is important, but also understanding the limitations of a file and how it works. In this particular case, you could ask, is this a real picture or a real animation? And it looks kind of cartoonish, so you would tend to say no. but you may need to be able to look at it a little bit more carefully and go, okay, by looking at the data file, I can tell that it's an animated GIF. I can tell that because of the header, etc. And I can tell that this likely was actually based on a real picture because of the following things, etc., etc. And so the ability to deconstruct the file and understand what the file really is and what it's really telling you is important. And so it's not a matter of just finding the right viewer for a particular file. As an example, a picture of me in my younger years, along with my wife, and you can see they're actually two separate pictures, but we put them together, and while by today's standards it's a pretty primitive technique and it's pretty obvious to see how it was done, there are better and better techniques that would make this much more difficult to detect, and so you may find yourself having to look at these things in a much more robust way. Now, the actual storage media itself. This is another one of these things, like the computer, that tends to be overlooked in a lot of cases. Again, it's a great place for finding physical evidence. It's pretty hard to install a hard drive without leaving fingerprints all over it, and that could be really useful. And it's not unusual to find DNA on USB drives and even some hard drives, externals, and that sort of thing. And so that's important. Likewise, lots of media have serial numbers which may be somewhat traceable, so that's another good source. So storage media themselves can be important. In this particular case, the hard drive that you see, this came out of a search warrant on a extortion and bombing case in North Carolina. And this hard drive contained a small cookie on it that was used by the subject to access his internet bank account in Latvia. And he knew he had to have this hard drive in order to access that account, which is where the extortion money was supposed to go, but he didn't want to leave it in his hard drive in case it was searched. So he removed the hard drive, packaged it exactly how you see in a Ziploc bag, and taped the Ziploc bag to a hanger and put a sweatshirt over it in his closet. And that's where we found it in the search warrant. And the fact that he had done all that, and the fact that his fingerprints were all over the hard drive, and the fact that that software key was on the hard drive was really devastating evidence at trial as to what he had done. More and more, the network is really becoming as big a deal as anything that's on the desktop, and arguably we're somewhat reaching the age where most of the data is going to be on the network and little of the data, relatively speaking, is going to be on the desktop. A good example of that are a lot of the tablets and things like the Chromebook, which have minimal operating systems and minimal services and minimal storage on the device itself, but access to virtually unlimited amount of data in the cloud. And this whole notion of cloud computing and the whole notion of virtualization as well adds a whole new layer of complexity to digital forensics. And there is a new and exploding field in cloud forensics. And what exactly does it mean from a forensic perspective, from a legal perspective, but also from an information security perspective? And I always encourage people in information security to think about how would you do forensics in a cloud? And it's not a simple answer. And in many cases, it's going to require the participation of the cloud provider. Now, given that that cloud provider may be a multinational, that might be problematic. So it's something to consider. Now, the other thing that I would suggest to you is that because we need to protect our networks more and more, there are many more security devices attached to networks. And we tend to monitor our networks more than perhaps we did. This is an example of Zone Labs' desktop firewall, but I use it only because you see the same sorts of things on dedicated firewalls and firewall appliances, intrusion detection system devices, both host-based and network-based, and all of the bastion hosts and that sort of thing. These logs basically track the connections within a network, and making those connections is important from a forensic perspective. But how do you collect all that stuff, and then how do you actually go to analyze it? It becomes less an issue of data collection and more of an issue of how can you actually do this. And that's why there are more and more very expensive commercial tools that will collect this kind of data and analyze it for you. And so this is a growth field in the information security arena. The other thing to keep in mind about storage media, by the way, is that there's a lot of different ways of slicing that problem, and we'll look at those in just a minute, or some of those anyway, in just a minute. The actual physical media itself, this is the old way that drives actually were encoded. The solid bars in the middle were actually the timing marks, and the forks that you see up there were actually the MFM encoded ones and zeros. And you can see that some of them are a little fuzzy on the tips, and that's because magnetic heads are mechanical devices, and they have a little bit of play in them, and so some of them go a little bit farther or not so far in each pass, and so you have kind of some shadows of what was there before by looking at the edges, which is why you were told to use multiple writes to clear a drive, format a drive securely. Now we have a little different drive structure now with the newer high-density drives. The actual magnets are located vertically, not horizontally, and so you can't use the same technique. But the notion that you might have to actually read physical media is one that has never quite gone away, but it's never really been terribly practical. But at least is a theoretical possibility, and it's one to keep in mind. There is one exception to this, and that's in the cell phone arena. In many cases, the high-end, the highest-end examination of the hardest to access cell phones is actually done by physically reading the ones and zeros that are in both the storage area and also the operating system for the smartphone. And that is a technique that, while not very common, is unfortunately essential in some of these high-end cases. As we've seen, there are really three, if you will, loci, three places where you tend to find information: the victim system, the perpetrator system, and the network devices. And you need to look at all of those layers, from the people all the way down to the physical media, on both the victim and the perpetrator systems, but also to the network which connects the two, and all of the places where the data is stored in between. So you're really talking about the network, the cloud, and cloud storage. And we can use the standard OSI model, and you're probably very grateful that I'm not going to sit here and discuss the OSI model in any great depth. But it's important to realize that each layer in the OSI model, or whatever network model you happen to use, has the potential for providing you with different information. And interestingly enough, Owen Casey's first version of his digital evidence book actually broke it down using the OSI model. I don't think the latest version does, but it was a very interesting approach as to what you could learn from each of these layers. And I think the principle is still good, whether or not in practice it's very easy to do that. But it may help you to visualize and understand what you're asking for and what you're seeing when you use something like Wireshark to look at the network traffic. Am I looking at something that came out of the transport layer? Am I looking at something that came out of the session layer or the presentation layer? In network forensics, there's really two things that you basically try to do. You either try to dissect packets and figure out what's in them, or put a bunch of packets out of a stream back together again in the correct order. The combination of those two techniques are really the building block of network forensics. And this is beyond the scope of this class, but it's important to realize that that's the basic principle. Well, this has been a very quick and dirty approach to this. I hope it hasn't been too terribly boring, but I wanted to give you really a framework for looking at all of the elements of digital evidence, a framework that you can use as technologies change and as methods and the use of technology changes. Well, I appreciate your attention, and until next time, have a good day.